Hello friends, we are going to continue our discussion on block electrons. In the previous lecture, we solved the energy eigenvalues of block electrons. We found that unlike free electrons, energy spectrum of block electron is gapped. We defined band gap as the energy gap between the two bands at the first Brillouin zone boundary. In this lecture, let us try to understand the origin of band gap in a 1D lattice. Remember what we discussed in basic quantum mechanics lecture. If there is a potential barrier, part of the incident wave gets reflected and the rest is transmitted. In a lattice, we are dealing with barriers repeated periodically in space as shown in the diagram. Let us try to calculate reflection due to the periodic potential. We expand the wave function in terms of just two Fourier components, e power ikx and e power ik minus bx. Note that if k is greater than 0 and lying in the first Brillouin zone, then k minus b is less than 0. In that case, e power ikx is the incident wave traveling from left to right in the lattice. E power I k minus bx is the reflected wave traveling in the opposite direction of the incident wave. To estimate how much is reflected, we need to calculate the ratio of ck minus b and ck. And for that, we need to solve ck and ck minus b. We are writing the Fourier series expansion of the wave function, keeping just two terms, e power ikx and e power ik minus bx. Time-independent Schrödinger equation is converted to a system of linear equations in case of block electrons. Note that other than ck minus b and ck, rest of the coefficients are 0. Because we have decided to keep only two terms in the Fourier series expansion of psi. We get two equations and we have to solve two unknowns, ck minus b and ck. From the second equation, we can write u times c k minus b is equals to epsilon minus lambda k times ck, which implies that ck minus b by ck is equals to epsilon minus lambda k divided by u. We also get the energy eigenvalues of block electrons from the system of linear equations as given here. Now, let us calculate this ratio. From this equation, we can write epsilon minus lambda k is equals to lambda k minus b divided by 2 minus lambda k divided by 2 plus minus lambda k minus b minus lambda k divided by 2 whole square plus u square whole power half. And then we divide by u, and this is equal to lambda k minus b minus lambda k divided by 2u plus minus 1 by u lambda k minus b minus lambda k divided by 2 whole square plus u square whole power half. And then we just rearrange the terms and take u inside the square root and write it as lambda k minus b minus lambda k divided by 2u whole square plus 1 whole power half. So this is the ratio of C k minus b and C k. So ratio of C k minus b and C k tells us how much of the incident wave is getting reflected because of the periodic potential. Now we write k is equals to b by 2 minus delta k, where delta k is the distance from the first Brillouin zone boundary shown by the green line in this diagram. We are going to rewrite this equation in terms of delta k. This is equivalent to changing our reference point in the reciprocal space. If we express in terms of k, the reference point is the gamma point. This one, which is the origin of the reciprocal space. If we express in terms of delta k, the reference point is the first Brillouin zone boundary shown by the green vertical line in the diagram. If we write lambda k minus b in terms of delta k, then we get lambda k minus b is equals to lambda minus b by 2 minus delta k, which is equals to h cross square by 2m b by 2 plus delta k whole square. Similarly, we write lambda k in terms of delta k. Lambda k is equals to h cross square by 2m b by 2 minus delta k whole square. Subtracting lambda k minus b and lambda k, we get this term. So let us do that. Lambda k minus b minus lambda k divided by 2u is equal to h cross square by 2m 2b delta k divided by 2u. Now we write the ratio in terms of delta k, that is C k minus b by Ck is equals to, so this term we have written in terms of delta k, so just replace that, h cross square b delta k divided by 2 mu plus minus square root of h cross square b delta k by 2 mu whole square plus 1. Now let us rewrite this term. So h cross square by 2m times b delta k by u. This is equals to h cross square b by 2m, and then I just multiply with b by 4 and 4 by b times delta k by u, and then we can write this as h cross square by 2m b by 2 whole square times 4 delta K divided by BU. Now note that this is equal to lambda P by 2, the energy of free electron with wave vector B by 2. So we write it as 4 lambda B by 2 divided by U times delta K by B. Now we replace this term in the equation of Ck minus B divided by Ck. So that is Ck minus B divided by Ck is equal to 4 lambda B by 2 divided by U times delta K by B plus minus square root of 4 lambda B by 2 divided by U times delta K by B, and then we have a whole square plus 1. Now we can slightly rearrange the terms and express Ck minus B divided by Ck in this form. Using a simple Python code, let us plot this equation, which tells us how much of the incident wave is getting reflected because of the periodic potential. We take A to be equal to 1, and delta K lies in the range of 0 and pi by A as defined here, and B is equals to 2 pi by A as defined here. We plot for 3 different values of U equal to -1, -1/3, and -1 by 9. The functions to be plotted for 3 different U's are defined here in the code. This is the code for plotting reflection due to a periodic potential. So this is the range of delta K. We are going to find the reflection for 3 different potentials, and the functions to be plotted are defined here. So let us run the code and see the output. Using a Python code, we have plotted the ratio of Ck minus B and Ck. The green dotted line shows the Brillouin zone boundary. The blue dotted line marks the region where K is very close to the Brillouin zone boundary. The purple dotted line shows the location of the gamma point. Now we find that if K is exactly equal to the Brillouin zone boundary, then there is 100% reflection, as shown here. If K lies near the Brillouin zone boundary, the reflection is very large. As we move away from the Brillouin zone boundary, the reflection decreases. When K is near the gamma point, the reflection is minimum. We find that for a given K, smaller the value of U, lesser is the reflection. However, there is a notable exception. If K is exactly equal to the Brillouin zone boundary, we always get 100% reflection irrespective of the value of U. We know that in case of free electrons, there exists no reflection. Thus, we conclude that block electrons with K far from the Brillouin zone boundary are free electron like. In this slide, I summarize our main findings from the numerical codes. We have calculated reflection of block electrons due to the periodic potential. We have found that how much of the incident wave is reflected depends mainly on the wave vector k of the block electrons. If the block electron has a wave vector equal to the first Brillouin zone boundary, it cannot propagate inside the crystal. This is true irrespective of the value of U. It does not matter whether U is small or large. Block electrons with wave vector equal to the first Brillouin zone boundary gets reflected 100% due to the periodic potential. If the wave vector is close to the Brillouin zone boundary, the lattice allows a small part of the wave to be transmitted. Amount of transmission depends on the value of U. If the wave vector is close to the gamma point, that is the center of the reciprocal lattice, then a large part of the incident wave is allowed to be transmitted. In conclusion, the lattice acts like a filter, allowing block electrons having K close to the gamma point to pass and not letting block electrons having K close to the Brillouin zone boundary. Thus, block electrons with K close to the gamma points are more like free electrons. However, as K value of block electrons move closer to the Brillouin zone boundary, its behavior starts deviating from that of free electrons. Comparing the energy of free and block electrons, we find a similar trend. Close to the Brillouin zone boundary, as shown by the red dotted line in the figure, energy of block electrons and free electrons differ significantly. However, close to the gamma point, energy of the block electrons is very similar to the energy of the free electrons. In conclusion, when the block electrons can propagate like free electrons, their energies are very similar. However, when block electrons cannot propagate like free electrons, their energies differ significantly. Propagation of block electrons are stopped because of the reflection by periodic potential, and we observe a gap in the energy spectrum of the block electrons. Is there any connection between the reflection and band gap? Let us investigate. So far, we did a Fourier series expansion of psi in this form. Now, we want to find out what happens to some incident wave with k equal to the first Brillouin zone boundary, that is k equal to b by 2. Substituting k equal to b by 2 in this equation, we get psi of x is equals to c b by 2 e power I dx by 2 plus c minus b by 2 e power minus I dx by 2. Time independent Schrodinger equation is converted to a system of linear equations of this form. We set all the c's to equal to 0 except for c minus b by 2 and c b by 2. Multiplying the second row with the column, we get this equation, and multiplying the third row with the column, we get this equation. Thus, we have two equations and there are two unknowns, c minus b by 2 and c plus b by 2. Note that lambda of b by 2 is equals to h cross square by 2m b by 2 whole square, and lambda minus b by 2 is equals to h cross square by 2m minus b by 2 whole square. Thus, lambda b by 2 is equals to lambda minus b by 2. And we just write lambda b by 2 in these two equations. For non-trivial solution to exist, the determinant should be equal to 0. Let us expand the determinant. Lambda b by 2 minus epsilon whole square minus u square is equals to 0. This implies that e square minus 2 lambda b by 2 plus lambda b by 2 square minus u square is equals to 0. Thus, the energy values are 2 lambda b by 2 divided by 2 plus minus half square root of 4 lambda b by 2 square minus this plus 4 u square. And we can write energy is equals to lambda b by 2 plus minus u. Thus, at k equal to b by 2, the difference of energy between the first and second band, which is defined as the band gap, is equal to Eg equal to 2u. Let us write a code and plot the wave functions. We take the distance between adjacent direct lattice points to be equal to 1, such that the reciprocal lattice points are 2 pi apart from each other. We assume that C b by 2 is equals to 1 by square root of 2, such that C minus b by 2 is plus 1 by root 2 in one case, and C minus b by 2 is equals to minus 1 by root 2 in the other case. We plot psi x is equals to 1 by square root of 2 e power I pi x plus 1 by square root of 2 e power minus I pi x in one case, and psi x is equals to 1 by square root of 2 e power I pi x minus 1 by square root of 2 e power minus I pi x in the other case. This is the code for plotting the wave functions. First, we plot for plus as shown here. Let us run the code. The solid red line is the real part of the wave function. The solid blue line is the imaginary part of the wave function. The dashed blue line is the probability density, and the red dotted vertical lines denote the location of the lattice points. Next, we plot for the other wave function by changing plus to minus. Let us run the code. Thus, we have plotted for psi x is equals to 1 by square root of 2 e power I pi x plus 1 by square root of 2 e power minus I pi x, and psi x is equals to 1 by square root of 2 e power I pi x minus 1 by square root of 2 e power minus I pi x. Clearly, both the wave functions satisfy Bloch theorem as well as periodic boundary condition. Bloch theorem is satisfied because the probability density has the periodicity of the lattice. Periodic boundary condition is satisfied as the wave function and its first derivative is continuous at the boundary. Clearly, the first wave function is cos of pi x. If we write in terms of the reciprocal lattice points, we can write as cos bx by 2. On the other hand, the second wave function is sin bx by 2. We get the wave functions in this form because of complete reflection at the Brillouin zone boundary. In the next lecture, we shall discover the link between such wave functions and band gap.